Alright, this is Lab 5, Breaking with Faraday by Hiley. So for the intro of this lab, the purpose of this lab was to investigate Faraday's law by analyzing the behavior of a magnet falling through an aluminum tube. And this experiment is going to demonstrate the relationship between a magnetic field and the induced electromagnetic force that opposes the motion of the magnet. And some of the fundamental laws that we're going to use in this lab are Faraday's law, Lenz's law, and the conservation of energy. So the model is that the aluminum tube is going to be assumed to be a perfect, like an ideal tube, so no resistance, and it's a conductive material. And the magnet is going to be modeled as a dipole with a uniform magnetic field. Some assumptions we're going to make are that the induced currents are in different sections of the tube and they do not interact with each other, and other forces like air resistance are going to be considered negligible. So the system of this experiment was a bar magnet, the tube, and the electromagnetic fields, while the surroundings are everything else. So the experiment involves dropping a magnet through a aluminum tube, and we're going to record it with a camera so we can analyze like the time of entry and exit after. And we're going to do this through 5 different trials to observe the effects of the electromagnetic induction on the magnet's motion. So our experimental time was 0.86 seconds, but actually the calculated time was around 0.7. And here are all the measurements for the tube and the magnet. And here's a video of the, and these are the checkpoint questions. So why can't we use a Ferris tube? So a Ferris tube has different magnetic properties which would interfere with the experiment, and this would make us not be able to evaluate the effects of electromagnetic induction. And what happens to the magnet if it's falling in free space without a tube? So if it's falling through free space, it's going to fall at a constant acceleration because there's no other resistive forces. But if it was falling through a tube, there are resistive forces like induced currents. And here's a closed script code. So the first part of the code just includes like all the initial values and creating the tube itself. And the next part of the code involved like functions for the dipole of the magnet and flux, which I think one of these was used in lab 3. And then the next one was the visualization of the tube, like the colorful stuff, and and the calculations of the time. So what if the resistivity of the conductor was reduced to almost 0, and if it was reduced to almost 0, the induced currents in the tube would be a lot larger, and this would create a much bigger opposing magnetic field. So what if holes or slots were cut into the tube? So if holes or slots were cut into the tube, this would interrupt the current pass and it would reduce the induced currents of the ring. Alright, so some potential sources of error that we could have had in the experiment was 1, calculating the times of the entry and exit times of the magnet. So it's kind of hard to do over video, so there's definitely could have been error there. And some more errors that could have occurred were that the magnet had inconsistent positioning, or that the tube was held incorrectly. So in conclusion, this lab demonstrated Faraday's law by observing the effects of electromagnetic induction on a falling magnet through an aluminum tube. And this experiment highlighted how induced currents generate opposing magnetic fields that slow the magnet's fall, which aligns with what we know about Lenz's law. And by measuring the fall time and analyzing the behavior of the system, we can see how these two laws interact with each other, and we can see the relationships between changing magnetic field and the electric field in a real life scenario.